second keynote speaker, Dr. Feifei Li. And there's no doubt that cloud has disrupted the database market. And it's probably one of the hottest topics in database system in the past 10 years. And you may wonder what's new about cloud databases and what role that our academic can play and what will be like in the next 5 or 10 years. And today we have Feifei, who probably can answer this question, but actually he is the one of the world leader who is able to answer this question because he has done tremendous great job in both academics and the industry. So Feifei Li is currently a vice president of Alibaba Group, director of the database product business unit of Alibaba Cloud, and the director of the database lab of Damo Academy. He was a full professor at the School of Computing, University of Utah, before joining Alibaba in 2018. So he might be very familiar with the award session we have because he has won multiple awards from ACM and IEEE and others. He is a recipient of ACM SIGMOD 2023 by the Paper Award, EDBT 2022 10 years Test of Time Award, IEEE ICDCS 2020 by the Paper Award, ACM SOCC 2019 by the Paper Award runner-up, IEEE ICDE 2014 10 years Most Influential Paper Award, ACM SIGMOD 2016 by the Paper Award, ACM SIGMOD 2015 by the System Demonstration Award, and the IEEE ICDE 2004 by the Paper Award. He has been an editor, PC co-chair, and core committee members for many prestigious journals, conferences, and technical meetings. So he has led the R&D efforts of building cloud-native database systems and products at Alibaba, such as cloud-native database VLDB and cloud-native data warehouse AnalyticDB, which propels Alibaba Cloud Database to be named a Cloud DBMS market leader by Gartner 3 years in a row. He's an ACM, CCF, IEEE fellow. So without further ado, let's welcome Feifei.
All right, so thank you so much. Thank you for inviting me to give a keynote at VLDB 2023. It's a great honor and pleasure to be with the community together. So I will be talking about cloud databases today. In particular, I will argue that database systems need to be modernized in the cloud era, especially with cloud, big data, and AI. There are a lot of opportunities for us to explore and build. Essentially, my key takeaway I want to give to you all is that building databases and running databases eventually will be just like playing with Legos. So here is the outline of my talk. I will give a quick overview of the key challenges as we have observed and opportunities in the era of cloud for building database systems. We identify in particular those 4 key trends. Then I'm going to use the key product, VLDB, to demonstrate how we go along addressing those key challenges. Then I will give a conclusion and future outlook. So first of all, a brief history of where the journey for database systems since the 60s and 70s. So if you look at this graph, basically what I'm trying to show you is that my argument is database system sits in the middle of application and hardwares in between. So any innovation in the hardware layer and any new applications in the application layer, those two will be the driving forces for us moving forward. That has been the case in the past 30, 40 years, and that's going to be the case for 10, 20 years down the road. So we started with hierarchical database, relational database, open source database, data warehouse, then NoSQL database, then all the way to cloud databases. And then we have witnessed hardware change from mainframe to a mini computer, then PC, servers, LAN, then to internet, then to cloud. Then application, of course, changed along the way as well. So the one argument I will say that database will no longer be standalone software as we used to understand it. Eventually will be, and increasingly we're moving toward computing as a service and data management, data serving as a service. So these are some of the key challenges if you ever play or build or serve database as a service on the cloud. So for example, increasingly, business application require processing from T+1 to T+0. That means you really need to get real-time interactive response to the applications. You are facing dynamic workloads. You have complex queries. You have highly concurrent workloads. You have data security issues. You have highly frequent transaction processing and needs for highly reliable service and zero downtime. Those are some of the key challenges as we see. And on the other side, I showed the key values provided by cloud databases, such as performance, elasticity, scalability, data fabric, end-to-end data governance, and so on and so forth. So this slide shows you from 10,000 feet what we are talking about. Databases start with the one to the left. We have those monolithic machine. We build database system for that. And oftentimes, if you deploy that in production, you do have to have primary and secondary setup. Right? Then you do data replication somehow in between to ensure high availability. Then we move to the cloud. Then we have essentially two different routes people have taken. One is the shared storage, share everything architecture in the middle. The other one is this share nothing distributed scale out to the right. So different architecture, of course, feature with different characteristics. As quickly summarized here, the single node DBMS is performant because it tightly controls and adapts to all the hardware resources available to it. But on the other hand, similarly because of that, exactly because of that, it has very limited scalability. Share nothing databases is introduced to address this horizontal scalability issue, but you do have to address the challenge associated with distributed transaction, distributed commit. In our experience, if you have more than 5% or 10% of distributed commits with the share nothing database systems, then oftentimes the performance degrades is very significant. It's very significant. So people then explore this shared storage, share everything database system, especially in the era of cloud computing, because we can now build massive shared cloud storage. Then we can decouple computing resources from storage resources. Of course, there is downside to that as well, limitation to that as well, which is, for example, it relies on special networking infrastructure such as RDMA. And because of that, the scale-out capability actually is also limited in some sense. So moving on from the architecture point of view, then now we move from application point of view. As recalled in the very first slide, I showed that the database innovation comes from both the hardware innovation and application requirement. We just talk about the hardware architecture change. Now we look at from the application side what business applications are demanding from us. It used to be we can just have cloud-hosted databases. That has been the case of traditional on-premise database as well. Essentially, you predict your workload and you provision enough resources for it. Essentially, that's what the first picture shows. Then when you move to the cloud, application require you to be elastic so that to be economic in the resources they're using. So we introduced this share storage, share everything, decouple compute storage architecture to deliver the figure in the middle, which is you have an initial quota provisioned resource for the application, then it changes over time like a staircase curve. And once you go down that path, you quickly realize that's not perfect. I want to be perfect. I want my resource provisioned at the moment, at any given point in time, match almost perfectly for the resource actually needed for the application being executed, which is the two figure to the right-hand side. Of course, this is challenging. If you don't do it right, for example, when serverless is first introduced, if you didn't do it right, application may get disrupted because you predict the resources not so accurately, or your elasticity is not so good to catch up with the change in the resource required. So luckily, we have done a lot of work. Community come together. Now we are in my opinion, Cloud Native 2.0, where serverless can really nicely predict the resource being required and offer this elasticity as we'll be talking about in this talk in seconds, so that we can really start with what we call quota-less and match a resource dynamic change of resource almost perfectly over time. OK, that's the overview part. Now let me move on to the second part. Given those backgrounds, what are the 4 key trends that we should be aware of? I'm not arguing those are the only 4 key trends we should be worrying about, but definitely these are the necessary conditions for us to move to the cloud era, move to the AI field. So what are those 4 key trends? So I argue that there are 4 key trends that we all need to pay attention to. One is to embracing cloud-native architecture. The second is to do full integration. Embracing of cloud-native architecture is mostly from the kernel engine system aspect. But that's not all the story. You not only you need to build the database, you need to actually deploy and maintain and run the database system over time. So the second trend is really to do full integration with cloud platform and orchestration. The third trend is, once upon a time, we all dream about building, one-size-fits-all system. Now you can do TP, AP, everything together. I will argue, that dream is probably not going to be coming true. So we won't have a single silver bullet solving all our problems. However, having different engines, like one for TP, one for AP, or one for AI workload, that's fine. But it's crucial for us to make data fabric work, to co-design those engines so that data can flow seamlessly without limitation. So that's the concept of data fabric. So that's the third trend. Lastly, of course, AI. Yejin talked about AI, large language model, NLP this morning. I will be talking about how we can integrate AI with database systems as the last trend. So under these 4 key trends, some of the key technologies, as we have witnessed in the last 5, 6, 7 also years, cloud-native HTAP, serverless, multi-master when you build cloud-native databases, and enterprise-grade, such as integration with security, cloud platform, AI, and then distributed. How do you combine distributed processing with cloud-native architecture? Those are some of the key technologies, and I will be going over some of them in my keynote talk today. Ultimately, when we address all these key challenges, when we deploy databases on the cloud in production environment, what is the ideal world going to look like? We argue, you're going to build and deploy database system just like playing with Legos or running with Legos. So as shown in this picture here, you have your storage, and even at the storage layer, you're going to have different type of storage. You have SSD-backed cloud storage. You have object storage that's low cost but less performant. How do you place them side by side? And then at the memory layer, how you disaggregate memory from compute node. So it's not just about disaggregation of compute and storage, but disaggregation of storage, memory, and compute. And then as a compute layer, you're going to have TP node, you're going to have AP node, you're going to have HTAP node, you're going to have AI node. Each of this is almost like a Lego piece. And it's all about how you can assemble them, build them independently, and assemble them in such a nice, seamless fashion, and you can even orchestrate them in real time, so that you can meet dynamic and different workloads without much effort. Okay, so that brings me to the main session, main course of my keynote talk, which is I'm gonna demonstrate those challenges and the work we have been doing. In our production database system called VLDB, I'm going to use VLDB as a running example, essentially, to reiterate, basically emphasizing those points I have highlighted. So a quick overview of VLDB. VLDB is a cloud-native database system we have built, and is publicly available on our cloud platform. So all the stuff I talk about today, you guys can actually try out. We have free trial instances available. You can try PolarDB afterwards on our public cloud platform. So it has 3 different versions. One is PolarDB for xScale, for distributed version. And then the other 2 versions are shared storage, shared everything architecture, one based on MySQL kernel, one based on PostgreSQL kernel. So the case study starts with trend number 1. Going back to the trend I was talking about, embracing the cloud-native architecture. I also list the set of papers we published around these topics so that you can dive into details if you want to after the keynote. So under this trend, I further divide into 3 different pieces. Let's start with storage. Database, don't take me, I think everybody understands this crystal and clear. Database starts with a good storage engine. Without a good storage engine, you don't have a good database system. So let's first look at what's required for a cloud-native database system. What is required for a storage engine? The big picture is, let me start with big picture again. Let's go back to this picture. Of course, this is a different aspect of what I actually talked about at the beginning. So we started with monolithic machine. Then we go to virtual machine with remote disks, the one in the middle. Then we go to shared storage, decouple compute and storage. Then we go all the way to decouple storage and memory. Of course, decouple of storage memory doesn't mean compute nodes do not have memory at all. They do. They still have local memory. It's just that in addition to the local memory they all collectively access to a shared remote memory cluster. And that's decoupled from the compute node and the storage. So ultimately, you have the architecture all the way to the right. That's how storage evolves for cloud-native databases. So now, get into the details. This is what it looks like for PolarDB. And I guess it's similar to other cloud-native databases over there, but there are many critical differences. For example, in the storage layer, do you use binlog to synchronize data across remote storage, or you use redo log to synchronize data between different remote nodes. Those actually make some critical differences. So we are going from these 2 decouple of storage and compute in the left-hand side. We go from there to the decouple of storage, memory, and compute on the right-hand side. Okay? And of course, it goes without saying, in the storage layer, in the shared storage layer, all cloud-native database systems use either a version of Raft or a version of Paxos to do data synchronization using distributed consensus protocol to make sure you have high availability at the storage layer. That's almost like a default. Okay. And also, there's another thing that's almost like a default, which is in front of the kernel, there is a proxy that acts like many important tasks goes to that proxy, such as load balancing, decouple write and read, and so on and so forth. Okay. Now, if you look at in details of the 3-tiered architecture, we have a shared distributed storage. Then we have a shared distributed memory, and in that shared distributed memory, there are critical challenges to be addressed, which I will be talking about later on, which is how you ensure essentially a global, consistent memory. So when you do read and write, how do you ensure the global memory cluster has consistent copies of the data from the local memory associated with the compute node? That's a really challenging problem. And how do you ensure transaction processing are satisfied with respect to certain isolation level? Mostly in industry, by default, we're using snapshot isolation. Seldomly, rarely, I see business application require serializable isolation. Typically, snapshot isolation is good enough. But in order to do that, you still need a global timestamp service, right, to ensure the logical order, like Lamport clock, of those transactions. Okay. Then you have the compute node. Of course, in the compute node, now the first generation of cloud-native database is one read and write node. The rest are read-only nodes. But that's essentially a waste of resources if you think about it, because many of your nodes are not doing much of your work. You still have the single bottleneck processing transaction at that one read-write node. So how do you scale that into multi-master? All the nodes can do read and write. And furthermore, can different nodes function differently? Can some nodes do analytical heavy workloads so that you have a hybrid row store and column store with that in-memory cluster? Those are some of the challenges and some of the interesting stuff we've been doing. So if you go into further look at the stuff I talk about, essentially, this is essentially the latest PolarDB looks like. So we have shared storage with Raft, with parallel Raft. Then we have the shared compute pool of resources. Of course, those are provisioned in an elastic fashion over time. Then there's the remote memory cluster that each compute node can access. And both shared storage and the shared memory are interconnected with the compute node using RDMA network. And another critical important detail that I want to mention is we do using redo locks again and again in data synchronization in both the memory layer and storage layer. We abandon the bin log approach because we noticed that like some other cloud-native databases, they started with bin log. The problem with the bin log is a logical log. So when you do data synchronization, when you replay data from bin log at the remote node, if you have write-intensive workloads, the replay cannot be done in parallel because it's bin log. It's logical. It's not physical. If you do redo, it's at page level. Then you can do replay in parallel. That's ideal and is important for catching up data in write-intensive scenarios. Of course, I noticed that there was some recent interesting work, I think it's last year, about replaying bin log in parallel, but I haven't seen that done in production systems yet. There's some interesting ideas there to explore. OK, now, if you look at cloud-native storage design, I put traditional storage and cloud storage side by side. So you know exactly what's going on. Local access versus remote access, local bandwidth with aggregated bandwidth, and so on and so forth. OK, and what are some of the key challenges? In one of our, I think it's the VLDB 2022 paper, we identified essentially 7 different challenges associated with designing a good cloud storage for cloud database systems. Of course, here comes another important piece, I will argue, that you have to keep in mind there are really 2 types from what I can tell. Of course, there are tons of different designs out there, but there are only, in my opinion, there are two designs that make all the way to mainstream production systems. One is B-tree-based design. The other is algorithm tree-based design. I haven't seen anything other than these 2 in a production system out there. Of course, B-tree and algorithm tree, they favor different scenarios and different contexts, as outlined in this table. I'm not going to go into details, but there are essentially what log you need to worry about. There's log replay you need to worry about. There's data rate. There's data rate you have to worry about. There's synchronization you have to worry about. All this goes under the big challenge of remote access once you do decouple storage and compute. Then there is this aggregated bandwidth problem. There is consistency among nodes, I/O isolation, and each of this, the way we view it is we decouple these challenges from with respect to B-tree and LM tree, because one is update in place, one is append-only updates. So for each of these challenges, how you address them with respect to B-tree, with respect to algorithm tree, can differ dramatically. That's essentially what I'm trying to argue. So some of the key techniques we've been using of attacking those challenges is to do thread-level parallelism. I actually give a detail of this, which is, for example, adopt multiple logging and data I/O threads using asynchronous asynchronous I/O model to fully scatter data across multiple storage nodes. Task-level parallelism, reduce remote and prefetching as much as you can. Fine-grained locking and lock-free data structure. In fact, we find the work done by Microsoft a couple of years, 10 years back, the BW tree is such an excellent data structure for building lock-free data structure in production systems. So we use that too. Of course, we did a lot of enhancement to that. And scattering among distributed nodes, bypassing cache if you can, and prioritize your I/O tasks. do fine-grained control over that. I don't have time to go into all the details, but I will say one thing, which is we talk about scattering IOs and do asynchronous IO as much as possible. I'll give you one example. The traditional warlog of any database system is sequential IO in nature, and it has low bandwidth utilization. So what we have done in PolarDB is when we access the shared storage, when we push the warlog to the shared storage, we actually do log partitioning. We partition the warlog. And we partition in such a way such that each partition can be written to the shared storage in parallel without conflict. So that's how we did it. So we do log buffer partition, then we enable parallels writing, and then we use this multi-threading, asynchronous multi-threading approach to push those logs to the shared storage. And this not only improves the utilization of your CPU, but also improves the utilization of your aggregated network bandwidth. And a scattered I/O across multiple remote nodes. It's a shared storage, but beneath the surface is distributed machines, right? So if you can scatter them around, you actually get better I/O performance as well. And the other thing we did is combine B+tree with LSM tree in a production system. Because if you think about it, they are really designed for different application scenarios. And why don't you try to combine them to get the best of both? What I mean by that is for warm and hot data, you use B+tree to do in-place update. Of course, we integrated things like BW-tree into our B-tree implementation so that we have log-free or latch-free data structure over there. But then for those archiving part of the data, like data over a month old, business applications seldomly access them in a real-time interactive fashion, but they do access them somehow. So the way we do is, you have a threshold somehow, then you push those data to a log structure merge tree, a storage engine we call X engine. And then you can combine the two. You can even build learning algorithms to decide when to phase out data from B-tree engines to LSM tree engines. Then the LSM tree engine is eventually merged and packed and puged to object storage, for example, like OSS on our platform or S3 on AWS. That's essentially what we have done. We also did partition table due to time interest. I won't have time to go into the details of that. Let's now move on. Once we understand storage better, now let's look at another really, really important piece for cloud-native database, which is serverless. I show this animation here, so you get a clear understanding of the difference between serverless database and first-generation cloud-native database. As you can see, the animation shows you clearly what's going on. So in order to deliver that nice animated picture over there, what you have to do? You have to do in-place scale up, like this one here, and you have to do cross-machine scale up. When one physical machine doesn't have enough capacity for you to keep scaling up, what you have to do? You might have to migrate the instance in warm and hot state to another machine so that you can keep scaling up, because machines come with different configurations, just like bin packings. And if that's not even sufficient, you have to do cross-machine scale out. Scaling up might not be sufficient. You have to do scale out. So all of this needs to be done carefully to support the serverless as we envisioned. So how we did it with PolarDB. Let's go back to this three-tiered decoupled architecture I talked about. So we have a shared storage. We have a compute resource pool. And each compute node does have its own local memory, but at the same time, they all access a shared remote memory pool. And we designed this data structure we call slab. A slab is nothing but a unit of memory allocation. In our setup, it's 1 GB by default, and implemented as a page array with 16K kilobytes pages. So essentially, it's just a contiguous page space. Each page is 16 kilobytes, and by default, it's 1 GB slab. So you have multiple slabs. And there is a home node, which is a slab node by itself, but with some metadata information. That's what it is. And then, essentially, the RW node and RO node will have its local memory, it's called local buffer, and they all access the global buffer. The idea is, it's kind of like local buffer is acting like caching now. And all you need to do at this point to support that serverless as we envision is to ensure local buffer consistency with the global memory buffer. Essentially, that's what you have to do at this point. And I show you some details. If you have that architecture, what you have to do cache invalidation. I won't go into the details, but essentially, it's essentially a detailed version of what I have just said. How do you ensure coherence, consistency between local buffer and that remote global memory? And when we do this, we want to ensure snapshot isolation. The way we did it is we designed a new data structure associated with each node. We call this CTS log. CTS stands for centralized. It's kind of like a timestamp oracle, TSO. So it's a centralized timestamp service. When transaction starts, it has to request a CTS. It's monolithic, incrementally maintained. So essentially, it gives you a global ordering and determine the visibility when a transaction tries to read or access a page. Essentially, that's what it does. And there's this particular data structure down below that has transaction ID, row ID, CTS, and so on and so forth to keep track of the changes and modification you have done to any page. And then the detail is to basically how do you validate the visibility of a page and consistency of those pages between local buffer and the global buffer using this design. The details is in this slide and also available in the paper. OK, with all that being done, what can we achieve? As you can see, now we can do second-level elasticity with PolarDB with all those design. So the first one shows you auto scale up of compute resource. The second one shows you auto scale out with compute resources. OK, as you can see, we can do scaling in seconds, in a matter of seconds. And not only we can scale up, we can also scale down. The first one shows compute resources. This one shows you memory resources. This is the throughput of PolarDB serverless while we scale out with remote memory. When we change memory from 8 gigabytes to all the way to 128 gigabytes, then we scale back down. And we also compared the design of two-tiered disaggregation, like storage and compute, without a remote memory, versus the one with a remote memory cluster, three-tiered disaggregation. As you can see, the difference is actually huge. The three-tiered disaggregation does help you dramatically in achieving much better elasticity. OK. Now, the last part of 21 I'm going to talk about is now we have serverless. What other challenges we have to address? Now, if you think about cloud-native database, now you get the big picture. You have shared storage. You may or may not have a shared memory pool. Then you have compute nodes. But what does those compute nodes do? Well, in the default setup, as I mentioned, the first generation, you have one compute node does all the transaction, read and write, and the other guys only do read-only workloads. Fine, but not ideal. Can we do multi-master? Like what Oracle RAC has done at one point, right? How can we move those Oracle RAC-like structure? Essentially, to keep it short, can we build a cloud-native version of Oracle RAC? And then can we do strongly consistent reads among those RAC nodes immediately? Once you allow multiple writes happen at the same time across nodes, the naturally next question is, can you ensure strongly consistent read under that? OK, so again, we're seeing this again, three-tier architecture with a CTS log, with the slab of memory and stuff, and local buffer. This is just a refresh of what we have been talking about. And now, what we're going to do is, based upon this, we're going to introduce another thing called multi-master fusion service. And this service sits together with that remote memory cluster, the shared memory buffer pool. So in that shared memory buffer pool, we're going to introduce this so-called multi-master fusion service. And what does this multi-master fusion service do? Well, it mainly attacks three key problems. One is buffer fusion, transaction fusion, and log fusion. Essentially, once you allow multiple writes happen at multiple remote nodes, in that global shared memory, you need to fusion them together. You have to fusion those conflicts together. Essentially, that's the key idea. It's actually not that complicated, but it all relies on this three-tiered disaggregation approach. Three-tiered disaggregation approach with a shared remote memory buffer pool. So buffer fusion is to have a shared global buffer pool to ensure cache coherence. Transaction fusion is to maintain a TSO, timestamp oracle, and transaction isolation over multi-masters. And then log fusion, sorry, the last one should be log fusion, there's a typo over there, is to ensure global transaction concurrency control. So this one gives you some of the details, a little bit of detail how we actually did it. So whenever you have, for example, a new page being created or a page being deleted, the local buffer needs to register or unregister that with the page fusion service. And whenever you have a transaction start, you have to get a global timestamp from the transaction fusion service from the TSO. And then whenever you have updates or commits to those pages, you need to synchronize with the global buffer pool to do page invalidation or validation, to essentially determine visibility between particular transaction and particular page. Essentially, that's what it is. Then this fusion service guy, polar fusion service guy, talk to, on your behalf, synchronize with the shared storage down below. OK, that's how we did multi-master, and you can see the results. Now we can achieve not only read linear scalability, but we can now achieve write linear scalability with a cloud-native database. When you scale out nodes, and you can see the throughput. These are write-intensive workloads. Now, naturally, the next question, we are database folks. Once you allow multi-master, the next thing is, can you ensure a strongly consistent rate? Of course, if you don't care about strongly consistent rate, you can also always do, you can always downgrade to read committed isolation level. Like you can even do read stale data, meaning allow a I/O node, allow a compute node to read out of date values if you are not dealing with mission critical application. But what if you do? Like in finance applications, what if you do? You deposit your balance. You want to, seconds later, you refresh your app. You want to see your balance right there. What do? This is what we call strongly consistent rate. So most cloud-native database by default, they actually give you return stale data, only ensure eventual consistency. OK? But of course, this doesn't manifest a big problem because, first of all, not all applications are mission critical. Second, this problem only surfaces when you have highly concurrent workloads. OK? So how do we ensure strongly consistent rate if we want to rest in peace? Now, let's go back to our design. By now, I think we are pretty familiar with this design architecture here. So we introduced yet another mechanism to do this, what we call hierarchical modification tracker. And then we use Lamport clock to synchronize between read and write, ensure this logical sequence of read and write. So what this hierarchical tracker does, essentially the idea is the idea is actually pretty straightforward. In a naive solution, you can just implement Lamport clock with multi-master, then you are done. You can guarantee strongly consistent rate. But the downside of that is the overhead is too much. So we essentially take a Lamport clock implementation, but make it in a hierarchical fashion. So we track a global timestamp and we check timestamp first at table, then at page level. So we check the logical ordering using Lamport clock in a hierarchical fashion. Essentially, that's what we do. This helps us dramatically improve performance while ensuring logical ordering. Essentially, that's what we did. It's quite a straightforward idea, but dramatically improve our performance in practice. Oftentimes, you are done checking at the table level. You don't have to go all the way to the record row level as a typical Lamport clock will do. Essentially, that's what it is. Here are the results. As you can see, the PolarDB SCC achieved almost ideal performance as PolarDB read stale, meaning that you don't ensure a strongly consistent rate, but with that hierarchical clock, with hierarchical lamp clock checking mechanism, even if you enable strongly consistent read, it performs just as good as read stale data. That's essentially what this experiment tries to tell you. Now, let's move on to trend number 2. I'm done with trend number 1. Let's move on to trend. Now, you build the cloud-native database. What's next? Well, you have to deploy it. It's a production commercial system. You have to deploy it and orchestrate this in cloud environment. So the trend number 2 is you really have to do full integration and orchestration with cloud platform. So this is the real architect of what's going on with Alibaba Cloud database orchestration system. We are now 100% Kubernetes with containers. We are 100% with Kubernetes and containers. And the thing with container is you have different ways of implementing these containers and to implement isolation between them. We used to do this, what we call run C container. We use C group to basically to do kind of like a spinning sharing of the CPU clocks. This is a soft isolation between process and application. This one is fine, but it really doesn't give you physical isolation between tenants. So you may have potential security issues if one compartment is compromised. So we introduced, for that, with regard to that, we introduced another thing called run D. There is a paper talking about that as well. And this gives you physical isolation in the container layer. And together, depending on your application, you can choose either run C or run D. If you have really strong security requirements between multi-tenancy, you should definitely go with run D. It's a little bit more overhead. It's a mini hypervisor, essentially. But it gives you much better security guarantee. Run C is essentially just using C group. Then we're using Kubernetes to organize all these pods. Either run C or run D. In the eye of Kubernetes, it's just a pod. Just a pod. Of course, pod of potentially different size, but they're just pods, like bin packing. Now it's become a bin packing problem. Now, if you think about this, then on top of that, we build out other essential services, such as backup, high availability detection, failover detection, stuff like that. Okay. Now, this goes back to the main theme of my talk again. Not only database kernels, database systems are like Legos. Now, orchestrating them become like playing with Legos, because each pod is a Lego piece. Each pod is just a Lego piece. Each container is a Lego piece. Of course, it's just that each Lego piece may look different in size, or in the kernel running inside those might be different as well. But it's just like playing with Legos now. Now, once you understand that, the natural question next is how do you do resource scheduling and allocation? Now we're balancing between the two, which is if you want to reduce cost, which as a cloud service vendor, we definitely want to reduce cost. We want to have a sustainable, profitable business. But at the same time, you are sacrificing customer, potentially, you are sacrificing customer experience while you try to reduce cost, because you may increase your resource allocation failure rate if you do that. So on one hand, it's resource availability. On the other hand, it's resource cost, provisioned resource cost. How do you balance in between the two using this quote-unquote Legos, those different pods and Kubernetes? So we designed this hierarchical resource management system. We have the online layer, we have the warm layer, we have the cold layer. And we call this system Eigen. Actually, it's going to be presented in this conference as well in VLDB. Essentially, we have different optimization strategy for different layers. For the online layer, essentially, we're solving a multi-dimensional bin packing problem. Why it's called multi-dimensional bin packing? Because each pod is different configuration. It's essentially a multi-dimensional bin packing problem. In the warm layer, essentially, you have to forecast short-term resource allocation. Essentially, for example, if the user comes to a region, asks for hundreds of VMs or containers with 4 core and 8 gigabytes memory setup, do you have the resource available to enable that in shortest amount of time available? So it's a resource prediction problem. Then in the cold layer is a long-term time series prediction problem. And there are tons of solutions for that. We don't have to reinvent the wheel. So essentially, once you decouple things, it becomes clear what technique you might employ oftentimes existing technique works just fine. You just need to carefully assemble them together to solve problem at each layer. So here are some results. I will just bring you to this. This is before we deploy Eigen. As you can see, we don't have a good balance between resource allocation rate and resource availability rate. But once we have those three-layer approach, we actually achieve a very nice balance between the two, between resource availability and resource allocation rate. The next part under trend number 2 is not only you do orchestration on cloud, you want to fully integrate with the cloud. I will argue this. Why Oracle built Oracle X-Data, Oracle RAC? Because Oracle realized it's really, really important to deploy your software system in control with your hardware system. Oracle realized that, I think, 10, 20 years ago. And I think this is happening again in the cloud layer. Cloud vendor, any cloud vendor, take AWS, Alibaba Cloud as an example. Cloud vendor, I argue, is going to be the biggest hardware distributor out there you can ever find. So it's important that when you deploy your software system, you understand the hardware system and you orchestrate nicely with that together, just like Oracle X-Data did 10 years ago. So there are a couple of new exciting directions I think we can explore as a community. One is Smart SSD. Smart SSD meaning that computational storage device. So far, the most common application I found with computational storage we found is for compression and encryption. Compression, decompression, encryption, decryption. We haven't found so much. People often talk about it, operator push down stuff, but I haven't found it common enough abstraction to do that with computational storage. But compression and encryption, yes. Why? Because you almost get a free lunch with compression, decompression down on computational storage, and REST as encryption is almost a default requirement by all business applications. So why don't you leverage on that? The second is different architecture for processors, ARM processor in particular. If you can co-design with ARM processor, oftentimes you get much better performance out of a standard x86 architecture. And then RDMA, we talked about that already. So I show you one example with Smart SSD. This is how PolarDB does for its compression. We are collaborating with Skillflux. Skillflux is a company that manufactures computational storage devices. So we push down compression, decompression to Smart SSD's device. The first generation used FPGA. Now we are using ASIC chips to replace FPGA, mainly in the interest of cost. FPGA is very costly, but ASIC is not so much. But of course, the trade-off is flexibility. Essentially, you push down those computational compression logical unit into this chip next to the computational storage. Now, suddenly you get compression, decompression done automatically along your I/O path. And we show you the results. We get almost similar performance with the normal storage device, but at the same time, we get, in the best case, we get 50, compressed data by half. Often, by default, on average, we can compress by almost a third, okay, without sacrificing any performance. And what are some other additional software hardware co-design opportunities? Well, there are SNA, smart network apparatus. Like, for example, nowadays you have programmable switch, network switch. You can push down some of the proxy processing to a programmable switch. And then you have CXL, Compute Express Link. My prediction is CXL will change memory landscape, the way we interact with memory, just like PCIe does for how we interact with storage devices. So that's my prediction. Of course, let's see whether that will hold true or not. But we are actively exploring this opportunity as well. OK, trend number 4. Data fabric. This is actually a very big topic. There are many interesting stuff I won't be able to talk about. For example, metadata sharing and the lakehouse. What I will be talking about is HTAP, because it's most relevant to the context of transaction processing databases. So if you think about transaction processing and analytical processing in big picture, there are essentially 4 different archetypes: row store, column store, separated row store, column store, but somehow you combine them together using ETL, or a hybrid, like what SAP HANA once tries to do, right? Hybrid row store, column store. So we explore both approaches, the hybrid row column store and the one with using ETL. But now we call it zero ETL. You will see in a minute what do I mean by zero ETL in that sense. The hybrid approach goes back to this. We are leveraging this three-tiered architecture again. We decouple memory. We have a shared remote memory. So in the shared remote memory, we are building a hybrid row column store. And we can convert data from row-oriented to column-oriented when needed. What do I mean by when needed? Because you are not doing analytical on all the columns. You are only doing analytical on a subset of your data. So only for those, we do this conversion. And once you have this hybrid store, you need to build a hybrid optimizer. So we change the typical path of a database optimizer. We have, obviously, a typical database optimizer has logical plan, cardinality estimation, CBO, physical plan, all that. Then we tweak this so that we can decide when to push to row store processing, when to push to column store processing. And then, of course, we implemented a vectorized execution engine so that we can leverage SIMD to speed up query execution as well. And the most critical challenge is to synchronize data between rows, the hybrid in-memory high store, row store to column store. We leverage log structure merge tree structure to do that. So it's, the row store continuously push data to this column store, but in front of column store, there is a log structure merge tree to buffer the append-only updates, then shuffle them into different groups to build the column index over time. Essentially, that's how we did it. And in this process, we are also using a redo log to do this. We are not using bin log to do this. The main reason for using redo log, as I mentioned a couple of times, is that it allows you to do parallel replay at the remote side. If you were to use bin log, parallel replay or bin log is a big challenge. There is no good solution, as far as I know, out there yet. And we evaluate this. We call this technique called in-memory column index. And you can see that, first of all, it has very nice scalability. And compared to the traditional PolarDB design, the PolarDB MCI can speed up. This is a TPC, kind of like a TPC-H kind of ish workload. It can speed up analytical processing very dramatically. The last part I want to talk about under this trend is the other approach, which is, what if I don't want to build a hybrid store? I just want to use a row store and column store separately. Traditionally, people are using ETL to extract, transform, then load data to the data warehouse. Increasingly, we find that in practice, in industry, people are going from ETL to ELT. So extract, load. I just synchronize. I don't do any transform whatsoever. And I just load data, synchronize data. Why that's happening? Because data warehouse system is getting more and more powerful. You can do transform on fly. You don't do transform in transition. You do transform on fly, relying on the powerful processing capability of those data warehouse systems. So essentially, that's what it is. All you need to do is use log to replicate data between the two. That's the trend we have observed. OK, I'm going to talk about, in the last 10 minutes, I will talk about the last trend, which is AI. It's such a hot topic. I think this can deserve a keynote by itself. So I will go really quick on this part. So essentially, we talk about AI augmented with database for I think by now, for 5-6 years at least in our community. There are really two directions. One is AI for DB, and the other DB for AI. So in AI for DB, essentially is for supporting intelligent database DevOps. So I'll give you a real example. This is one of the service we built on Alibaba Cloud Database Service called DAS, Database Autonomy Service. So it monitors critical performance metrics in real time, and to do root cause analysis, and then to interfere when something goes wrong. In this case, resource is under-provisioned, identify that, and automatically give suggestion and give you a correction plan. How we do this is increasingly, if you go to a real production system, you will know that today we are running databases with many, many microservices. I'll give you one example. So suppose operation 2 with service 1, you update that, and something goes wrong. So the execution time that get delayed. And because of that, it propagates all the way down. And eventually, service 1 realizes that there's a problem. But service 1 will have a hard time to figure out where along all these microservices, where things goes wrong. That has been a real challenge for us. So the way we address this, we borrow this idea from statistical analysis called Shapley value influence analysis, which is essentially, if you have a chain of events, you can use Shapley value to analyze the influence of one change to the downstream events. Essentially, that's what it is. We borrow this idea, we apply this to microservice debugging, and we actually get pretty good results. The other thing is tuning for database parameters. And there are a lot of different challenges over there. First of all, you have multiple components. You have resources, you have indexes, all this interplay with each other. How do we ensure when you tune them, the interdependency is carefully captured? And second, if you can address that. Second, how do you do tuning of databases in an online fashion and deploy this in real production system? Because tuning this in a backup offline instance is fine. But if you try to do this in real production system, especially for transaction systems, you cannot afford even a 1% rate of failure, right? So how do you do this? And then you have heterogeneous data as well. Data change over time, workload change over time. How do you address all these changes? So we actually propose different techniques for this. One is REST-tune, which essentially is to learn knowledge. A lot of things I actually resonate a lot with the keynote this morning by Yejin, because essentially what she was saying is that instead of build a big meta learner, right? What you do is you try to leverage structured knowledge as much as you can so that you can reduce the cost of learning. Essentially, that's what we've been doing as well. For example, in this case, to capture dynamic workloads over time and reduce learning cost, what we do is we find similar tasks in the past, and we assemble them. We build an assembled learner on top of historical tasks. Essentially, that's what we did here. To address the online tuning challenge, as I talked about, we realized that in today's database, almost all production databases are deployed with either Paxos or Raft. You have multiple replicas for you to use. You do tuning and deploy and test on those one of the replicas. You don't do this on the primary. And data is synchronized automatically for you by the underlying protocol anyway, right? So why don't you leverage on that? And then you can do this nice tuning online. There are other details as well, but you can then do this in an online fashion. The last one is what if you have multiple agents interfering with each other, resource, index, parameter value settings, and all that. Well, you know what? In algorithm field, there's this very classical problem called multi-amp bandit problem. Essentially, it's exactly the same abstraction. So you can borrow the same idea over there to database tuning. It's just model a multi-amp bandit problem. And then you are playing this exploit and explore trade-off game. Essentially, that's what it is. Lastly that's AI for DB. What about DB for AI? Well, there are two main trends as far as we can tell. One is load and run AI models inside databases. For example, load large language model, TensorFlow model, PyTorch model into your database and do inference with data inside databases. For example, you can do this nowadays in database, right? I asked PolarDB to produce a portrait of Mulan, and I further asked that portrait to be updated with the helmet for Mulan. You can do this using SQL, very simple. As long as you can import external model and store that model in databases, you can do this in SQL. The other big trend is natural language to SQL. Can you interact with databases using natural languages? For example, what's the average life expectancy in countries where English is not the official language, given the schema down below? Well, we propose a solution called Cat SQL. Again, that's why I find this morning's talk very resonate a lot with me. Of course, a baseline solution is to just use large language model. You can use large language model for this, no problem. But you're going to end up with much bigger, much expensive model to work with. If you can somehow capture and analyze the inherent knowledge and the structure of the problem at hand, in this case, a SQL understanding problem, SQL has structures. SQL has structures. If you can somehow capture that in the constructing model, you end up with much, much smaller model and much more effective model, too. So we designed this column action template to capture the structure of SQL. Essentially, we have the basic block, select where from clause. Then you have nested block. Then you have the aggregation block. So we basically build, essentially the idea is to build an encoder for each different structure you will find in a SQL. Then you combine those encoder together to form a language model for SQL. Instead of building one gigantic large language model as a spaghetti view of the SQL. So essentially, that's what we did. And the results is actually pretty, sorry, I'm going back. The results is pretty amazing. Now we can do this. You can just drag 3 tables, single age, single information, and their agency information. Then you can ask questions like this. Which singer has most popular songs than the average singers? Then you can get the results back with a very complex SQL being generated automatically for you. Now, how do we combine this with large language model? Large language is such a popular topic nowadays. Well, on the right-hand side, you can definitely use a large language model for it. But I would argue a better way of using large language model is the right-hand side, which is you build domain-specific models, also using encoders. So the technique is similar of like that building large language, but you combine that with large language models. So for example, in the context of demo I just did, instead of returning tabular results, you can take those tabular results and feed into large language model to generate a natural language response instead. So you can combine the two. The last piece, vector database. Vector database is becoming a pinecone, right? Milvus become really hot topic. I'm sure there were research group out there venturing about vector databases. Essentially, what vector database is to do embedding of unstructured data, and then you can represent unstructured data using embeddings, high-dimensional vectors. Then you can do fusion search. So this is a typical structure for including a vector engine into a typical database. You use a large language model to do the embedding, or you can use an open source embedding for that matter. And once you have that, you have this high dimensional vector, typically in thousands of dimensions. You have millions or thousands of millions of vectors. Then you have this vector database now. Then you can do similarity search. That's how you can integrate large language model with a vector database engine. Now you can build a chatbot, for example. And the most typical algorithm people use for vector database, there are many, but so far we have tested tons of it. But the most successful one is done by this work, Malkov and others from 2016. It's called Navigatable Small Word Graph, NSW. Then NSW essentially is building a proximity graph over the vectors. Each node on the graph is a vector. Then you build a proximity graph over these vectors. And to speed up the search process, you borrow the idea like a probability skip list, but you apply this idea of probability skip list over this NSW, Navigatable Small Word Graph. It's called HSW, Hierarchical Navigatable Small Word Graph. And you get something to the right. Most mainstream vector databases nowadays use this algorithm in their core. Then you can build database like this. You can have fusion search. You have vector search using vector index. You have filter conditions just like traditional database. Then you have text search. Then you can do this fusion search seamlessly in one database engine. of course, there are optimization here you can do. Like if you have 3 different conditions, which one you go first, which one you go afterwards. Looks like a new challenge, but guess what? This is very similar to old database. We have been doing this for years, guys. Like selectivity, physical path, which physical path you select is the same game. It's the same game. It's just under different contexts. That will conclude my talk. Before I conclude my talk, I will just mention security is big. I don't have time to talk about it, like confidentiality, authentication, compliance. There are many challenges if you try to deploy a cloud database a database in the cloud, as you can imagine. Unfortunately, I don't have time to go into detail of that, but we really, as a community, we need to pay attention to these issues. Now, let's come to my final concluding remarks. What I want you guys to remember from my talk. Before I give you that, I will argue that research innovation is important, but when you deploy a system in practice, I will argue good engineering practice is the key. For example, how do you do debugging? How do you do CI/CD? The Sigma best paper that we got this year is not about kernels, not about orchestration, but about debugging. How do you debug join queries, logical optimizations? We build this TQS, transform, query, synthesize. We borrow the idea from normalization. The idea is, when we learn database in high school, in grad school, we all learn normalization. Especially, we learn 2 things about normalization. What are they? Dependency preserving normalization, and the other one, lossless join decomposition. And we borrow the idea of lossless join decomposition, but we apply that with join query plan debugging. The idea is very simple, right? If you think about it, if you generate a logical plan, it has to be lossless join in order for that to be correct. So we twist the idea and we apply that to debugging. We got really, really good results. So PolarDB is open sourced. Of course, not everything I talk about today is open sourced, but we did open source the PostgreSQL version and the distributed version. So I highly encourage you guys to check out if you are interested. We had a book on cloud native database. We published the Chinese version of the book. We will publish the English version of the book. Now, the final slide. So I think these are some of the key takeaways if you think there's something useful from my keynote. One is computing the database will no longer be a standalone software. Increasingly, we will have computing as a service and data as a service. Hardware innovation is a key driving force for database innovation. And cloud vendor, arguably, will be the biggest hardware distributor over there. If you think about it, cloud vendor actually lower the barrier for distributing new hardware to the mass. Database system we won't have one-size-fits-all database system, but as I argued with Data Fabric, we're going to build different database engines, but you need to worry about, or you need to care about how to seamlessly integrate different engines together as a data platform and deliver that to your end users. Ease of use, cost effectiveness with FinOps, good engineering. Those are some additional things that outside research community people work really hard on. And AI, lastly, I will argue the current state of AI is nothing else but the summary and compression of data and knowledge, albeit unstructured. But if you think about it, database from day one is a summary and compression of data. So database and AI, naturally, they're hand in hand. So they will be hand in hand, and they will continue to be like that. So how do you deepen the integration of the two is going to be a really interesting challenge down the road. That will be all. I would say that the talk is a representation of collective work from my team, and also the support from the CTO division of Alibaba Cloud, which is now led by Jingren Zhou, he's also from our community. So thanks for that. Thank you.
We have 2 microphones on the ground.
Wow, that was information-packed talk. Thank you, Feifei. Do you guys believe in the notion of hybrid cloud where some information is in the public cloud, some information in the private cloud, and how to allow in a single query even combining information from these 2 different kinds of cloud?
Oh,
The
thank
IBM,
you.
as you probably know, when they bought, spending a lot of money, Red Hat, the claim was multi-clouds. No single cloud will take over the whole world. But also not all the data will move to the cloud was the assertion.
Yeah, yeah.
And
Excellent question, Mohan. So in an ideal world,
hey
if you
guys,
ask,
hello.
yeah, in an ideal world, Mohan, if you ask me, I want to live in a world where we only have public cloud. We don't have to worry about private cloud and hybrid cloud. Why? Because it's all about economy of scale, right? It's easier for us, it's easier for the customer, but unfortunately, we live in this real world, and where for some reason customer want to still have on-premise IDC. In that case, we do have to have hybrid setup. So Alibaba Cloud does offer that, and so we help customers set up a cloud environment on their on-premise IDC, and when their on-premise IDC run short of resources, they can choose to scale up. This up is up to the cloud, up to the public cloud. On Alibaba Cloud. So we have the support for that. But I will tell you, in practice, this kind of setup is super complicated. I mean, if from a technology research and engineering point of view, I will not argue for it. But from a business point of view, unfortunately, I'm paid, I have to do it. That's the reality of it.
The more specific thing I was interested in was, if you want to combine the data in a single SQL statement or a single database kind of context, has anyone thought about this in your company or anything that somebody else has done?
Yeah, I think like even, for example, AWS, I use AWS example. AWS, designed this product called Outpost, right? Essentially, you can extend. Outpost is a special device. You can deploy it in customers' IDC. Then you can certainly connect those and orchestrate those just like AWS Public Cloud does. We have something similar to that as well. We also have the hybrid cloud that you talk about, like when customers run short of resources in on-premise IDC, when they scale their resources up to the public cloud, we support that. But I will argue that in most of those cases, when customers do that, they realize there's a problem with that approach too. So what they do is they do it in silos, meaning that their public portion and their on-premise portion oftentimes are perfectly sharded, so that you don't have that much of coordination, communication going in between of the two. It's perfectly sharded setup, essentially.
No, but if you want to join information that's in the public cloud with the information in the private cloud, and you want to make sure that the private stuff never goes to the public cloud because of the security, whatever things, the database system has to be conscious of these sorts of restrictions, right? So it's that sort of thing that I was...
The last part is a response to your question, which is oftentimes both the user and us will design in such a way they are perfectly sharded. So the scenario you talk about, we try to avoid that as much as we can. So it's hybrid setup, yes, but the public cloud session and the private cloud session are oftentimes perfectly sharded. That makes sense?
In other words, you are saying you won't try to join.
We won't try,
but that, I don't know whether that's a user-friendly thing from a querying perspective and so on, right?
Well, yeah, so in most scenarios, we find that, when business application require hybrid cloud, typically it's a massive business application. And oftentimes in that business application, if you drill down carefully enough, you can partition the business logic in almost perfectly sharding manner, so that you can avoid exploring that dark water. Yeah.
Hi, I'm Sang-Cha from Seoul National University. So, well, thank you for the comprehensive coverage of this, the system that you built. Actually, I built SAP HANA more than 10 years ago.
Okay.
So we are addressing the same problem in distributed landscape, and essentially we are solving the same problem. You're repeating what we developed in a way, cloud context. You integrated the cloud features. So I'm glad to see that. Also, I'm glad to see that you also integrate this LLM stuff and the vector database inside, this server. So actually, we also did integrate the machine learning inside SAP HANA, so it worked. It was developed actually Wenshan Li at SAP China. So, that's also working well. So in a way, we got a new application, new context. So you're solving the problem. But,
exactly. I think you're absolutely right, because essentially a lot of challenges we're facing today, folks 10, 20 years have solved those challenges and just under different hardware setup. That's essentially, that's my view, I think.
So my question actually at the end is, what are the scalability? Let's say you have a single landscape. What are the scalability that you see? As the number of nodes added to the landscape, single landscape. What are the performance that you observed?
I think the big picture, you are absolutely right. I think the big picture is we can learn a lot from history, right? So just like you have Oracle RAC, you have SAP HANA. If you think about Oracle RAC, it's very similar to cloud-native databases. It's just that they build it on a siloed hardware environment. But now we're building this same architecture in a cloud environment. SAP HANA, hybrid row store, column store, again, in siloed hardware environment. But now we're building this in cloud hardware environment. Essentially, that's what's going on. And moving forward, the big landscape I would predict is, in my takeaway messages, new hardware will always find its first deployment in cloud, and it's important to leverage those properties in your design, and integration with AI will be the dominant topic for the next 3-5 years, at least, I think, for database systems.
Thank you.
Thank you. All right, thank you.